Hello, Miss Newen. This is my video for question number 3. So it says investigate these two, a sequence and a series we're given, and then we're to do our own, make our own and solve it. So generally you want to look for a formula. So the general formula I found was 1 plus 1 over n to the power of n. I found this because looking at the terms we're given, 1 and 1 over the two ones are constants, but you'll notice that the denominator and the exponent changes depending on each term, and they're also equal to each other. So 1 and 1, 2 and 2, 3 and 3, 4 and 4, and so forth. So we can assume that they're both a constant, and they're both the same constant. So I did 1 plus 1 over n, and then the exponent being n as well, because the denominator and the exponent are equal. Or equals in the sense that they're the same constant. So obviously I did some testing just to make sure the formula works, and I used the first two terms, term 1 and 2, and I in fact did get the same answer. And just to further the testing, I also inputted a value that's not in here, so we only got 4 terms, and I just did number 6 because we didn't get 6. So after you've come with your general formula, your f of x, or f of n, whatever, you wanna observe and see how it behaves when it is approaching the limit. So when x is approaching infinity. That's exactly what I did. And to do this, I just subbed in some larger numbers, so 10, 100,000, 10,000, just to see based on how the f of x, the y value, behaves. So, after this, the value doesn't really change from 2.718, just like the really, the fourth, the fifth, the sixth decimal changes. So I came to the conclusion that as x approaches infinity, y approaches e, and e is 2.71828 and so forth. So the limiting number of the sequence is the constant e, or 2.71828. and then for b, we're given a series. So these are numbers here, and just like the first one, you want to come up with a general formula to find the terms. So the formula I found, the way I did it was, first I found there's like a pattern in the denominators. So first I solved that, and I found that 2n minus 1 works, because initially I was just going to put 2n, but each one of these is an odd number. So 2n minus 1 worked for this pattern of 1, 3, 5, 7, 9. And I did check. So when I sub in 1, so for the first one, I do get 1. When I sub in 2, I get 3. When I sub in 3, I get 5, and so forth. However, the main issue wasn't the 4, and it wasn't the 1, but it was this minus sign over here that changes. It changes. Not that it's a constant negative sign. It goes from negative to positive in that alternating pattern. So what I did was, instead of just putting a 1, I put negative 1 to the power of n plus 1. Now, a negative number to the power of a positive exponent, like that, so negative 1 to the power of n plus 1, this will cause it to change from positive to negative to positive to negative, negative to positive, whatever, as the terms continue. So as it goes down, this will cause it to change. And this formula isn't for the sum, but what it gives you is each individual term. So if I subbed in 1, I would get that. If I subbed in 2, I would get this. If I subbed in 3, I would get this. I wouldn't get the total. I would just get this individual number. So this is an infinite series, and it goes on forever. So what I did was, I went and Googled an infinite series calculator, because obviously I can't calculate, up until infinity to find the exact number. Now, what the infinite series calculator told me was that this would give me a value of pi. And this does make sense, because before doing this, what I did was, I actually converted all these into decimals, and I added them. And what I got was a number very close to pi. So approximation dot, very close to pi. And upon further research, I came upon something called the Leibniz formula for pi. And the formula looks something like this. And you'll notice, oh yeah, it doesn't look the same as this, but you'll notice that ours give us an answer of pi. This one gives us pi over 4. So I thought, what happens if I take the 4 to the other side? And when I did that, you'll see that I got this formula, this series, sorry, the same one we're given. So the limiting value of this series is pi. So as x approaches infinity, let's just write that down. As x approaches infinity, y is going towards pi. So after investigating all this, the last question, the last part of this question, asks us to create our own series. So I just came up with this one: 1 over 2, 2 over 3, 3 over 4, 4 over 5. And from what I learned from investigating the other two is, first you want to find a general formula or pattern. And what I found was this, because I noticed that the numerator changes according to each term number. So 1, 2, 3, 4. So first term 1, second term 2, third term 3. And I noticed that the denominator is always 1 more than the numerator. So I found n to represent the numerator and n plus 1, since the denominator is always 1 greater than the numerator, to be the value for the denominator in the formula. So I tested it with 1, 2, 8, 9, and I did in fact get these values. So just like I did for the first one, I wanted to see the behavior on what would happen when x is going towards infinity. So I just plugged in some numbers, and I noticed a general trend that as the numbers get higher, f of x or y tries to gets closer and closer and closer to 1, but never reaches 1. So as x approaches infinity, y approaches 1. This is the limiting value of this sequence that I came up with. Thank you for watching.